All right. Hi, everyone. So before I get started, I'd like to extend a thank you to Prisma and the organizers for putting on this event. So Rust in Axle OS, what does that mean? So my name is Philip. Fun fact about me, I adopted a puppy this week. So my girlfriend is at home taking care of him. Thank you, Daisy. And I work for this company called Data Theorem. We do application security. I focus on like static analysis of iOS apps. And you'll notice this company logo in the bottom left of all of these slides. And what that means is that I got a free plane ticket to come here. So thank you, Data Theorem. Okay, so Axle OS, what is this? This is a project that I started many years ago, 2016. So it's been quite a while. It's a hobby OS, so it's not based on Linux or anything like that. It's just from scratch operating system. It targets x86-64. It's a microkernel, which means that as much as possible, like the file system, drivers is not in the kernel, which would be a monolithic kernel. They're instead pulled out into system services, into user space applications. And it's a single user system. And what that means is that this is a very lonely hobby. So just to give you a sense of, kind of where the system is at and what things are like, there's a little demo video here. So this is a UEFI bootloader, the pink screen here. Then we're going to boot into Axle's desktop environment. So this is the window manager. Now I'm opening the file browser, which, spoiler alert, is written in Rust. And just to show off a little bit, I'm going to run Doom and let that load and run around a little bit. Show you like dragging some windows around and resizing things, keyboard and mouse input, all pretty standard stuff, but there's a lot that it takes to get there. Axle is written in lots of C, way more C than I ever intended to write in my life, but here we are. And this comes with just really horrible, horrible bugs. And not only really difficult bugs in kernel space, but also it's just an ill-suited tool for a lot of the things that I want to do, building desktop applications, building kind of more high-level productivity software. It's just too difficult, and I was looking for a different tool to use. So I evaluated a few options. I looked at porting Zig, C++. Eventually, thankfully, I settled on Rust, and I ported libc at the end of 2021. So I've been writing a lot of Rust in Axle for about a year now, and now it's very much the language of choice for any new code in Axle. So since this is a lightning talk, we're just going to be talking about a couple of things. So the GUI toolkit that's used to write new desktop applications, and interprocess communication, or IPC. So this is Axle's kind of historical GUI toolkit, which is written in C. So you've got all the kind of standard widgets that you would expect in a GUI toolkit. We've got sliders, buttons, subviews, pixel buffers, all that sort of stuff that you would find in any GUI toolkit. And again, just to give you a sense, this is over on the right, we've got a screenshot of the logs viewer application. And then there's the code for it over on the left. Of course, it's in C. It's only about 30 lines. It's a pretty straightforward program. And there's a few things I want to point out here. So the text view, where all the logs are drawn into, it's global state. We've got this callback that's called a sizer callback. And so the way that this works is anytime the window is resized, this function will be invoked with the size of the parent window, and then it returns a rectangle that the text view should now occupy. Of course, since this text view is just the size of the window, it just returns the window size that was passed in. And then there's this message handler. So we'll talk a little bit more about this later in the talk, but I wanted to just briefly point it out now. This will get invoked anytime a message is sent to this program. So there's a bunch of drawbacks with this C GUI toolkit. It enforces the use of global state. It's really awkward to build just sort of standard UIs that shouldn't be really difficult to create. Everything is awkward, and of course, the major problem is no memory protection. Not unique to a GUI toolkit, just a C problem. So just as a little example of this, I've made a silly demo program. We've got two views, blue one and a red one. And the blue view is going to just turn all of its pixels white with a memset. The problem is it's a little bit overzealous with the memset. And you can see there's nothing at all stopping it from just overwriting all the other pixels in the view below it. And there's really nothing you can do about this in C. So I rewrote a toolkit in Rust. So over on the left, I've got a window using the C GUI toolkit, and on the right, a program using the Rust GUI toolkit. And if these windows look pretty much the same, that's really good. That means I've done my job, because these have totally different underlying implementations. And you know what? Before I move on here, could we just take a moment and check out those corners? You know what? Could we actually get the action cam on these? That would be yeah, thank you. Awesome. So I spent so many hours of my life getting the pixels on these corners just right for that little drop shadow effect, and then I had to do it again in Rust. So not fun, but hopefully the end result is, looks nice. And I wasn't kind of sure if I was going to show this because, it's no secret GUI toolkits in Rust are not an easy problem for a number of reasons. So the code is pretty gross, even in Rust. But I did want to point out, this is the code for that Rust window, of course, and then we've got that same concept of a sizer callback, a closure that gets invoked whenever the window is resized and says what the new size of the view should be. Cool. So here's the comparison. Here's some historical programs over on the left using the C GUI toolkit, and then over on the right, some newer programs written in the Rust GUI toolkit. So on the top there is a file browser. And then on the bottom is this IDE I've been working on where you can write x86 assembly, and then at runtime it gets linked and loaded into an executable program. The doc, you couldn't see it in that screenshot, but it's also written in Rust. One thing that I think is cool about the doc is it's just a window like any other. It's just a normal windowed application. There's a little bit of hacks in the window manager, so it doesn't, it can't be dragged around, and it doesn't have the title bar on it. But otherwise, it's just a window. OK, so let's take a look at the virtual address space mappings of each of these programs. So that top program is Axel's virtual address space visualizer. And then over on the top, we have the virtual memory mappings for the Rust GUI toolkit, and on the bottom for the C. Now, if we look at the virtual memory mappings here, we'll see some pretty standard stuff. Over on the left, we've got the code segment of each of these programs. Then we've got the heap, the stack. That 7 megabytes is then a frame buffer, and there's a 64 megabyte space that we'll talk about a little bit later. But one thing that you'll notice if you look at this, that seems a bit weird, is the memory usage for the C GUI toolkit is way higher than for the Rust. The heap in the C one is 31 megabytes versus just 20 kilobytes for the Rust one. Why is that? Well, in the C GUI toolkit, anytime you want to have a subview, you actually need to have a separate full-sized frame buffer. That is, it's a frame buffer the size of the entire screen. And then every time we draw the window, we composite all of those together into a final image. So the memory usage is, ridiculous with this approach. It's also slow because on every redraw of the window, you need a composite. And as we've seen, there's nothing stopping you from trampling on another view's pixels. So what would be nicer is if instead of having all these different frame buffers that we then composite together into a final image, we could have some kind of, slicing syntax where you could just get like a reference to a rectangle of pixels that you're allowed to draw into, and you wouldn't be able to draw outside of that rectangle. That would be really cool. Let's see if we can do that. So I wanted to use, so the idea here is each of these subviews would just get a rectangle, and you couldn't, draw into anything more than that. I wanted to use the index trait for this. Unfortunately, I couldn't do it because of that little ampersand. So this is sort of the bones of the trait that I ended up implementing for this. The idea is that anytime a subview recurses, anytime it wants to draw something else, you call this getSlice, and it returns a kind of smaller slice. And then you can use all of these methods and what you get back to gradually build up the view. So it's really cool. Right. Moving on to interprocess communication. So the all interprocess communication in Axel OS happens by way of this kernel subsystem called the Axel Message Center, or AMC. So we could take a kind of case study here and imagine how this might work. So say you've got a driver that's listening for events from like a PS2 keyboard that's plugged into the machine. And then, of course, that keyboard driver is going to eventually want to tell the window manager, which hosts all the windows, shows the desktop environment, dispatches input when the user does stuff. Of course, the keyboard driver is going to want to tell the window manager, hey, the user pressed a key. You should forward that to a window or otherwise do something with it. And the way that it does that is with this syscall, Axel Message Center message send. So it would send this key press event to the window manager. The window manager would then dispatch it appropriately. But of course, when the keyboard driver sends this event to the window manager might not be ready to receive it. The window manager might be in the middle of drawing some other windows, handling some other input. So of course, we're going to need some kind of queuing in place to deal with this. So the way that this works is that for every AMC service, there's a kernel-level message queue that it gets. So here we've got a view of those queues in the kernel, one for the keyboard driver service, the mouse driver, the window manager. So the window manager might have some might have some messages sitting in its queue. And then when the keyboard driver sends that message, it'll just go and sit in that queue. Then when the window manager is ready, it uses the await syscall to get a message out of that queue. And it's first in, first out, so it'll slowly work through all of the events that have been queued up for it until it finally gets that key press. So this is kind of the total syscall body. And what's cool is that this is actually the main syscall surface of Axel OS. Even if you want to do something like setting up a shared memory mapping, you just send a special AMC message to the kernel, and it'll know what to do. So of course, I've expressed this in a kind of Rustified syntax, but this isn't Rust code. These are syscall vectors. They have a totally different calling convention. But this is a Rust conference, so I wanted to give a sense of what the conventions were like for this via kind of Rustified syntax. And if you look at this, you'll notice, where is this going to go? Where is it going to sit in memory? Of course, it has to go somewhere if we're saying, give me a message. Where do we put it? So to visualize what happens here, we could kind of imagine the virtual address space mappings of a process. But if you tried to do this, if you tried to take the virtual address space mappings of a process and then lay them out, left to right into a diagram like this, you run into a pretty difficult problem. And in putting together this presentation, I had a lot of difficulty figuring out how you would kind of solve it. Thankfully, I finally figured it out. So the problem, of course, is that if you did try to lay everything out from left to right, it gets really cramped. So what I did was I turned it 90 degrees. So that's all solved. And now we can just list the virtual memory mappings. So of course, at the bottom of the address space, you've got the null page. Then you've got user mode code. Directly contiguous with that is the stack. The heap, then the stack higher up. You've got kernel mappings that are shared in every process. In Axel OS, we do a thing where we take physical RAM and we remap it in a high memory. So that's sitting around. And then there's one more memory mapping that's really important here. So you have this thing called the AMC delivery space. So what will happen is, I was a bit speedy. When the window manager uses that await syscall, what the kernel will do is it'll take a message out of that queue that's sitting in the kernel, and it'll memcopy it into the AMC delivery space. So to visualize this a little bit more, I've set up two kind of dummy programs, a sender and a receiver. So the sender, this is all the code for it, and we can walk through what it's going to do. So it's going to start up. Then it's going to register itself as an AMC service. Then it's going to send a message to the receiver, and the body of the message is just going to be the number 1. So the kernel queue for the receiver is going to have a 1 placed into it. Then it's going to send a 2, same thing. OK, so looking at the receiver, this is all the code for that. Of course, it's going to set itself up as an AMC service. And then it's going to call await twice to get each of the messages. So the first time it calls it, the kernel, as we saw, is going to memcopy into the AMC delivery space. And now that's in scope. That's message 1 just over there. Now it's going to call await again, and it's just going to memcopy it again into the AMC delivery space. But message 1 is still in scope. The thing that it's pointing to has just been overwritten. This is not good. And to see exactly why this isn't good, I have this log line just down at the bottom. It's printing out the value of message 1 a second time after we called await again. And you can see, we get the first message, it has a value of 1, second message, value of 2, and then when we reread the first message, it's been overwritten. This is a classic use after free. So of course, there's straightforward ways to get around this. For example, AMC message await could just copy whatever it receives to somewhere on the heap. But I thought this was kind of interesting that I didn't know if there was any kind of nice way to express in Rust that the thing returned by this is valid, until the next call to AMC message await. And I would be interested to hear if anyone has ideas on how to express that. I also wrote some other stuff in Rust that I thought I would mention. So I wrote a Game Boy emulator in Rust. This is the emulator running in Axel, running Pokemon Red. That was really fun. Rust is really nice for this sort of software. It's also really nice for just kind of holding, references to various things. And when they go out of scope, you can give them back to the OS. That's really cool. Recently, I wrote an AHCI driver in Rust. A bit tough to say. So what that is if you want to talk to a SATA controller, if you want to talk to an SSD, you have to use this protocol AHCI. So I wrote a driver for that. And Rust is, again, just so nice for this sort of software. It's been a really pleasant experience, especially coming from so much C. As I had a look at a few minutes ago, I wrote an x86-64 assembler and linker. I wrote the initrd file system in Rust, or rather rewrote it. And I also rewrote the initrd generator in Rust. And I have more plans for Rust as well. The window manager suffers from a few, memory corruption liabilities. So it'll be nice to rewrite that in Rust as well. There's a TCP/IP stack that I want to rewrite in Rust. It also has, other auxiliary protocols like DNS and ARP. So I want to rip all that out, rewrite it in Rust. I want to write a GPT disk formatter so I could get, a proper file system sitting on a hard drive. And I want to take that x86-64 assembler that I mentioned and put a C front end on it. Okay, a little bit ahead of schedule there. I hope I wasn't speaking too fast. Well, thank you, everyone. Yeah.
Thank you so much. It's a great talk. Do we have any questions? We have time for questions. Anything? Yep. Please speak in the mic.
Have you looked at the new const type parameters? Because that might be the solution for your little non-reusable, like for not overriding your message space, maybe?
I have not. What was it called?
I don't remember the exact name. Somebody will be able to correct me, but it's like you can now parameterize your type with const. So like maybe with an integer. So like if your function has like 0 as a parameter, then the space is already taken and you cannot override this. But if you free, you can increment this and you have like one space more. I'm not sure how it works. I did not play much with it, but maybe could be a solution to your little problem.
That's neat. No, I haven't seen that. Yeah.
On the same topic, what about, have you tried mutual exclusivity of mutable references for that?
What would that mean or look like?
So like in that, once you borrow mutably, you can't borrow mutably again until you drop the previous one, and so that would prevent you from having two in scope at the same time.
Cool. I don't know. I guess it's, it's mutable from the perspective of like the kernel can just memcopy anything it wants there, but it's not necessarily mutable from the Rust side.
Right, but I'm just saying like arbitrarily making it mutable on the Rust side to enforce that it's mutually exclusive.
Okay, yeah, that's a cool idea. Thank you.
Yeah. We have time for one more question. Anything? No? Okay, well, thank you so much.
Thanks, everyone.